Far out in the frozen expanse of space, 13 billion light-years from Earth, something truly unimaginable is staring back at us. The James Webb Space Telescope, exploring deeper into the universe than any instrument before it, has revealed phenomena that challenge everything we believed we understood. Ancient galaxies that shouldn't exist. Black holes older than time itself. Signals from rogue worlds echoing across the void. If you love uncovering the universe's deepest mysteries, Docuverse will take you on a journey that could forever change your view of reality. For decades, astronomers thought they had the universe's expansion figured out. Hubble provided one measurement, theoretical models predicted another. Everything seemed consistent, until Webb looked farther than anyone had before, and the cosmic puzzle shattered. The universe is expanding at two dramatically different rates, depending on where you measure. Picture a balloon inflating, but the top half stretches twice as fast as the bottom. That should be impossible. Physics dictates a uniform expansion. Webb confirmed the worst fears. When astronomers measured distant Cepheid stars, they received one result. Using the cosmic microwave background gave an entirely different number. This isn't a small discrepancy. It's so vast it shakes the foundations of our understanding. Scientists call it the Hubble tension, though the term hardly captures its scale. This isn't a mere measurement error. After observing over 1,000 Cepheid stars across 5 galaxies spanning 130 million light-years, the contradiction remains. Either our cosmic models are flawed, or some unknown force is distorting reality itself. Dark energy, the mysterious driver of cosmic expansion, might behave in ways we never imagined. Some regions of space may expand faster than others, stretching the very fabric of spacetime. Lead researcher Adam Reyes stated bluntly, with measurement errors excluded, what remains is the staggering possibility that we fundamentally misunderstood the universe. Exciting barely captures it. If our understanding of cosmic expansion is wrong, every calculation about the universe's age, size, and destiny is questionable. Webb's unprecedented precision leaves no doubt. This contradiction is real, and that was only the beginning. Webb's deeper survey revealed objects that shouldn't exist. Near the Big Dipper, astronomers expected tiny infant galaxies, but instead found 6 enormous, mature star systems, forming when the universe was only 3% of its current age. To imagine it, picture growing a full-sized oak tree in just 3 months. That's what these galaxies achieved on a cosmic scale. Star formation takes millions of years. Gravity needs time to gather gas and dust to ignite nuclear fusion. Yet these 6 galaxies accelerated their growth, becoming cosmic titans while the universe was still young. Each contains 10 billion to 100 billion stars, forming hundreds each year. Our Milky Way forms just 2 annually. Scientists have nicknamed them universe breakers because they defy all existing models of galactic evolution. Then came something even stranger. Webb discovered a supermassive black hole, Cuson, wandering alone in space, completely naked, without the billions of stars that typically surround such giants. Most supermassive black holes reside at galaxy centers, co-evolving with their hosts over billions of years. Cuson breaks all rules. It packs the mass of 50 million suns into a region smaller than our solar system, drifting through the early universe like a ghostly anomaly. Every discovery so far challenges our understanding of cosmic evolution. Docuverse presents these revelations in all their shocking, mind-bending detail. The universe is stranger, faster, and far more chaotic than anyone expected, and James Webb has given us a front-row seat. To put that in perspective, if Earth were the size of a marble, Cuson would still be invisible to the naked eye while containing more matter than exists in hundreds of billions of ordinary stars. What makes this finding truly unsettling is the timing. Cuson exists in the universe's infancy, just 600 million years after the Big Bang. Traditional black hole formation relies on the death of massive stars, meaning the first generation of stars must form, live out their lives, and explode as spectacular supernovas, a process that should take far longer than 600 million years. Roberto Maiolino, the Cambridge astrophysicist who helped identify Cuson, described the discovery as entirely off the charts. The object challenges every model scientists have created for how supermassive black holes grow and evolve in the early universe. 3 theories attempt to explain Cuson's existence, each more unsettling than the last. The first suggests that some black holes form directly from collapsing massive gas clouds, bypassing the stellar stage completely. The second proposes that intermediate mass black holes somehow grew at impossible rates by consuming matter faster than physics should permit. The third theory is the most disturbing. Cuson might be a primordial black hole formed in the universe's first seconds during violent fluctuations in space and time immediately after the Big Bang. If true, Cuson has been lurking in the cosmic darkness since the very beginning, waiting 13 billion years for stars and galaxies to form and reveal its presence. Cuson is one of hundreds of similar objects Webb has identified. These small red dots appear across the early universe. Each represents a potential cosmic monster that defies explanation. They glow with the light of matter being shredded and superheated as it spirals into their gravitational pull. The presence of these naked black holes indicates that the early universe was far more chaotic and violent than cosmologists imagined. Rather than a gradual orderly formation of cosmic structures, we might be witnessing evidence of primordial catastrophes that forged massive black holes before the first stars even existed. If Cone truly is a primordial black hole, it is something far older and stranger than any galaxy or star. But Cuson wasn't the only impossible black hole Webb discovered in the cosmic depths. Black holes older than the first stars are illuminating the universe and may have existed since the moment of creation. Scientists have long assumed that supermassive black holes formed after the first generation of massive stars collapsed. This process should take hundreds of millions of years. Gravity gradually pulls together enough matter to ignite nuclear fusion. Stars live their brief, brilliant lives, then explode as supernovas, leaving stellar remnants. But James Webb has found evidence of supermassive black holes existing when the universe was barely 400 million years old, far too early for the traditional formation process. Andrea Ferrara and his team at the Superior Normal School in Pisa, Italy, propose a radical solution. What if black holes, not stars, were the first major sources of light in the universe? What if primordial black holes formed in the chaotic first seconds after the Big Bang, already lurking in darkness while the cosmos was still young? These hypothetical primordial black holes would have formed via a completely different mechanism than stellar black holes. Instead of collapsing stars, they emerged from extreme density fluctuations in the primordial soup that existed less than 5 seconds after the Big Bang. Picture the early universe as a violently boiling pot of energy and matter, with some regions so dense they collapse directly into black holes without ever forming stars. Webb's evidence supports this extraordinary scenario. Many of the bright objects in the early universe appear point-like rather than extended, suggesting they are powered by compact sources instead of distributed star formation. Gas near a black hole heats to extreme temperatures and emits brilliant light. From a distance, this superheated matter can resemble starlight. If correct, primordial black holes were feeding on the universe's first gas clouds, growing larger and more massive while lighting up the cosmos. These monsters sat in darkness for hundreds of millions of years, essentially waiting for the universe to evolve enough to provide them with fuel. The implications are staggering. Primordial black holes could explain how supermassive black holes grew so massive so quickly in the early universe. They had a head start of hundreds of millions of years, allowing them to reach enormous sizes before the first galaxies formed around them. Yet this raises further unsettling questions. If primordial black holes were common in the early universe, they may still exist today, unseen and undetected. Some could wander through our galaxy, ancient relics from the universe's violent birth predating every star we see. These primordial monsters represent a major shift in our understanding of cosmic evolution. Instead of a universe gradually building complexity from simple beginnings, we may be observing a cosmos born with massive objects already embedded. Detecting primordial black holes would also provide crucial insight into the Big Bang's physics, revealing conditions in the universe's earliest moments. Webb's surveys of these ancient black holes revealed an even stranger phenomenon, challenging our understanding of gravity. Two galaxies are colliding in a cosmic crash, generating physics never observed before. When astronomers first noticed the object they called the Infinity Galaxy, its form immediately drew attention. This cosmic oddity displays two compact red cores, each surrounded by glowing rings, forming a perfect figure-8 pattern resembling the infinity symbol. But this unusual shape was just the start. The infinity galaxy formed when two massive disk galaxies collided head-on in a cosmic smash millions of years ago. Galaxy collisions are common, but this particular event created something unprecedented. Instead of a chaotic merger destroying both originals, these galaxies preserved their identities while creating something entirely new. The bizarre aspect is the supermassive black hole's position. Normally, central black holes spiral toward each other, merging or ejecting one. The infinity galaxy breaks this pattern. The supermassive black hole sits between the two galactic nuclei, suspended in a vast expanse of glowing hydrogen gas stripped during the collision. This position should be unstable. Gravity should pull it toward one nucleus, not leave it floating like a cosmic referee. Peter van Dokkum and Gabriel Bramah, who discovered the system, believe they are witnessing direct collapse black hole formation. Instead of forming from massive star deaths, this black hole may have formed directly from the collapse of a massive gas cloud during the galaxy collision. The process works like this. The two galaxies collide, producing enormous gas streams between their cores. Under the right conditions, these streams can become so massive and dense that they collapse directly into a black hole without forming stars. It's like a cosmic avalanche creating its own gravitational trap. This mechanism could explain one of Webb's most puzzling early universe discoveries. The telescope has found supermassive black holes too massive for their age, growing faster than traditional models allow. If black holes can form directly from collapsing gas clouds, they could reach supermassive status more rapidly than previously thought. The infinity galaxy serves as a real-time laboratory for studying this exotic formation. The black hole appears to actively feed on gas between the galactic cores, growing as the collision continues. Radio observations show intense energy emissions at the black hole's location, confirming it consumes matter. Yet the most disturbing aspect of the infinity galaxy collision isn't what's visible. It's what this suggests about the early universe's violent processes. If direct collapse black hole formation was common in the cosmos's youth, the universe went through a phase of immense violence and chaos we are only beginning to understand. That violence left behind objects even stranger than wandering black holes. Hundreds of orphaned worlds drift through space in pairs, broadcasting radio signals that shouldn't exist. James Webb has identified over 500 free-floating planets in the Orion Nebula that don't orbit any star. These cosmic wanderers, roughly Jupiter-sized, were ejected from their original systems and now drift through interstellar emptiness. Many travel in pairs, orbiting each other at distances 25 to 400 times that between Earth and the Sun. Scientists call these paired wanderers Jupiter Mass Binary Objects, or JMBOS. They challenge all existing planet formation theories. Planets normally form in gas and dust disks around young stars, slowly accumulating material. The gravitational choreography to create binary planets should be extremely rare, yet Webb found dozens of these cosmic couples. The mystery deepened when astronomers observed these paired planets with radio telescopes and discovered unprecedented signals. Several JMBOs emit radio bursts never before seen from planets. These aren't standard emissions from worlds with magnetic fields interacting with charged particles. They produce gigahertz frequency bursts thousands of times higher than FM radio. On Earth, such frequencies come from technology or highly energetic phenomena like pulsars and quasars. Their presence on rogue planets suggests physical processes absent elsewhere in our solar system. The radio emissions appear linked to the binary nature of these planets. When two massive objects orbit each other, they generate complex gravitational interactions that create powerful magnetic fields and electric currents. Think of it as cosmic friction on an unprecedented scale. If these forsaken planets are capable of emitting such intense radio signals, what other extraordinary phenomena might they host? Their magnetic fields could surpass anything within our solar system by orders of magnitude, generating space weather capable of influencing nearby star systems. Even more unsettling is what the sheer number of these paired worlds implies about planetary system formation. If hundreds of such binary planets exist in just one nebula, millions or even billions could be scattered across the galaxy. Each represents a failed solar system, a cosmic mishap where gravitational forces went awry and expelled planets into endless darkness. These rogue planets are cosmic orphans, eternally cut off from the warmth and energy of stellar companionship. They exist in perpetual night, their only heat stemming from the slow decay of radioactive elements within their cores and the tidal forces of their orbital waltz with their companion. Yet, as bizarre as these wandering planets are, Webb uncovered worlds that challenge our understanding of planetary formation even more fundamentally, forcing scientists to re-evaluate core assumptions about how planets emerge around young stars. One youthful star system defies conventional planetary formation rules, creating planets composed of unexpected materials. In the star-forming region NGC 6357, James Webb identified a planet-forming disk nearly devoid of water, yet rich in carbon dioxide, precisely where Earth-like worlds would normally arise. This discovery upends one of the most fundamental assumptions regarding rocky planet development. Standard planetary formation models predict that regions around young stars, where terrestrial planets form, should be dominated by water, ice, and silicate minerals. Water, abundant in the universe, is essential for producing planets capable of supporting life. The disk surrounding star JWST disrupts these expectations entirely. When Webb analyzed this system with its near-infrared spectrograph, astronomers anticipated detecting water vapor alongside familiar compounds. Instead, carbon dioxide dominates the inner disk regions, where terrestrial planets typically form. Water is so scarce it is nearly undetectable, creating an environment unlike any previously modeled. This finding fundamentally challenges our understanding of planetary chemistry. On Earth, water shaped geology, atmosphere, and life-supporting conditions. A planet forming in JWST 10 would develop under drastically different chemical circumstances, producing worlds without analogues in our solar system. Two hypotheses attempt to explain this peculiar chemistry, both with unsettling implications. The first posits that intense ultraviolet radiation from either the young star or nearby massive stars sterilized the disk, breaking water molecules and expelling hydrogen while leaving oxygen to combine with carbon. The second is even more disconcerting. The carbon dioxide dominance may arise from unusual conditions in the disk's dust grains. Unlike normal systems where dust is coated with water ice, these particles might instead carry carbon dioxide due to the young star's environmental conditions. Both explanations suggest planetary formation can follow pathways astronomers never anticipated. If UV radiation can remove water from forming disks, many potentially habitable worlds might never receive the chemical precursors needed for life. Consequently, the galaxy could harbor countless dry, carbon dioxide-rich planets formed under conditions hostile to life chemistry. This discovery also prompts questions about the diversity of planetary systems throughout the Milky Way. If planet formation can yield such divergent chemical environments, entire classes of planets may exist with geological and atmospheric processes unlike anything previously known. The XU-10 system serves as a natural laboratory for investigating alternative formation pathways. As its planets mature, they provide insight into how worlds develop when their fundamental chemical makeup differs radically from Earth's solar system. Yet this strange chemistry was only one of Webb's many atmospheric surprises. The telescope next targeted a world so alien and hostile it challenges our definition of a planetary atmosphere. A planet so close to its star that its surface glows like molten metal somehow sustains an atmosphere defying known planetary physics. 55 Cananke orbits its star so tightly it completes a year in only 18 Earth hours. Tidally locked, one side perpetually faces its star, creating a scorching day side capable of melting copper and a night side plunged into eternal darkness. Surface temperatures exceed 4,000 degrees Celsius, enough to vaporize most known materials. By every rule of planetary science, it should have lost its atmosphere billions of years ago. Yet Webb observed the impossible. This infernal planet retains an atmosphere composed of gases normally unable to exist at such extreme heat. The atmosphere is rich in carbon monoxide and carbon dioxide, forming a thick envelope around a world that should resemble Mercury. Discovery came through precise temperature measurements via Webb's mid-infrared instrument. Dayside thermal emissions were cooler than expected, indicating some mechanism redistributed the star's energy. Only a sufficiently thick atmosphere could transport heat from the blistering dayside to the frozen night. This circulation generates one of the most extreme weather systems known. Supersonic winds carry vaporized rock and metal from day to night, condensing as molten mineral rain. The day-night temperature difference, over 3,000 degrees Fahrenheit, is moderated by convection currents beyond earthly laboratory replication. The source of this atmosphere is equally extraordinary. It cannot be primordial. Solar winds would have stripped such gases millions of years ago. Instead, researchers suggest a secondary atmosphere, continuously replenished from the planet's interior. The crust itself is boiling, tidal forces from the nearby star literally cooking the interior, releasing carbon-rich material through volcanic outgassing. Stellar radiation destroys the atmosphere even as geological processes replenish it under extreme conditions, creating a hellish cycle where the planet feeds its own atmosphere. Rock vapor rises, blown by supersonic winds, condenses on the night side and rains down as molten metal and stone. The entire planet functions as a colossal distillation apparatus operating at the limits of physics. The presence of 55 Canan-Cree's atmosphere suggests planets can maintain gases under far more extreme circumstances than previously imagined, impacting our understanding of potentially habitable worlds. If atmospheres survive such hellish conditions, they might endure on planets previously deemed too hostile for chemistry to persist. Yet this infernal planet was merely a precursor to Webb's next encounter, an interstellar visitor challenging our perception of time itself. An ancient comet from another star system races through our solar system, older than Earth, the Sun, and everything we call home. Comet 3I Atlas appears modest at first, 7 miles wide, composed of ice and rock, following a path past the Sun before returning to interstellar space. Detailed web analysis revealed an impossibility. This visitor is approximately 7 billion years old, 3 billion years older than our solar system. Its steep trajectory indicated origin from the Milky Way's thick disk, a region filled with ancient stars from the universe's youth. This wanderer drifted through interstellar space before the Sun even glimmered in stellar nurseries. Predating Earth, Mars, Jupiter, and all planets in our neighborhood, Webb's near-infrared spectrograph revealed the comet's coma dominated by carbon dioxide rather than water vapor typical of solar system comets. Traveling over 130,000 miles per hour, it could cross the United States in under 2 minutes. Its flat, straight path defies solar system norms, following the galaxy's gravitational rules rather than the Sun's. 3I Atlas embodies a messenger from an era when the universe was radically different. 7 billion years ago, the Milky Way was more chaotic and violent, star formation rates were higher, heavy elements scarce, and planet-building chemistry distinct. The comet formed around a star long dead before our Sun existed, surviving its parent star's violent supernova and wandering the galaxy for 3 billion years, a frozen time capsule of ancient chemical signatures. Its observation raises unsettling questions about how many other ancient visitors may cross our solar system unnoticed. 3I Atlas is only the third confirmed interstellar object, though models suggest dozens or hundreds may traverse our neighborhood simultaneously. Each represents a fragment of a destroyed world, a piece of cosmic history surviving unimaginable catastrophes, an artifact of stellar systems from the universe's youth, conveying information unobtainable from any other source. Finally, 3I Atlas reminds us of our solar system's eventual fate. In billions of years, solar winds may eject objects into interstellar space, becoming wanderers puzzling astronomers in distant galaxies long after Earth ceases to exist. The ancient comet's arrival offered a glimpse into cosmic timescales far beyond human comprehension. Yet Webb's surveys revealed phenomena even stranger than interstellar visitors from extinct star systems. Some 300 enigmatic objects glow in the early universe, baffling astronomers. James Webb's deep observations uncovered a new class of cosmic bodies that defy classification. Tiny red specks like crimson pinpricks pepper the early universe's imagery. Their characteristics are so peculiar that scientists struggle to categorize them. Each is far brighter than expected, given our understanding of galaxy and star formation in the universe's infancy. The mystery begins with their color. In astronomy, red light usually signals extreme distance or cool temperatures. These objects are undeniably distant, existing when the universe was under 1 billion years old. Yet they radiate tremendous energy through unknown mechanisms, producing a blend of traits unmatched in the modern cosmos. Using infrared imaging and spectral energy distribution analysis, researchers at the University of Missouri identified 300 such entities in Webb's data. Each appears roughly the size of early galaxies, but emits far more light than galaxy formation models predict. If they are galaxies, they are unlike any existing today. Their extreme luminosity forces scientists to rethink early galaxy formation. Conventional models assume the first galaxies grew slowly, accumulating matter through gravitational collapse over hundreds of millions of years. These little red dots imply that some process generated massive, luminous structures far faster than current theories allow. The puzzle deepens when astronomers attempt to pinpoint the source of this light. Some appear point-like, hinting at supermassive black holes rather than widespread star formation. Others display extended structures, suggesting rapid galaxy-wide star formation. The most unsettling possibility is that they represent a previously unknown phase of cosmic evolution. During the universe's first billion years, conditions were radically different. Matter density was higher, dark matter interactions more frequent, and the large-scale cosmic web still forming. Perhaps these circumstances enabled forms of object formation impossible in today's universe. Certain red dots emit X-rays, ultraviolet and infrared light in patterns indicating violent, chaotic energy production. Whatever drives them operates under extreme conditions, pushing physics beyond familiar boundaries. These objects appear randomly distributed, rather than clustered in expected early galaxy formation zones, suggesting they may reflect a fundamental property of the young universe. Graduate student Bang Jiang Sun stresses that even confirming a few of these objects in the early universe would require revising galaxy formation theories. The sheer number Webb has found implies our grasp of cosmic evolution in the universe's youth is incomplete. These little red dots pose perhaps Webb's greatest cosmological challenge, yet the telescope's next revelations regarding the universe's large-scale structure were even more astonishing. Galaxies across vast regions spin in coordinated patterns, hinting the universe itself may have been born rotating. In Webb's potentially most mind-bending discovery, astronomers observed galaxies separated by millions of light-years rotating in sync. This cosmic choreography contradicts our understanding of structure formation and suggests the cosmos may have an inherent rotational direction. Observations of 263 galaxies in Webb's deep extragalactic survey revealed orientations and spin patterns that defy standard cosmology. Distant galaxies, too far apart to gravitationally influence each other, rotate in similar directions. It's as if every windmill across a continent turned identically, despite no coordinating mechanism. Distances between these galaxies are so vast light takes millions of years to traverse, yet all participate in the same cosmic dance. Computer scientist Leo Shamir proposed two unsettling explanations. The first, the universe was born rotating. If the Big Bang possessed angular momentum, it could have imposed a preferred rotational direction on subsequent cosmic structures. This aligns with black hole cosmology, suggesting our observable universe may reside inside a massive black hole within a larger parent universe. If accurate, Webb's observed rotations could reflect the parent black hole's spin transmitted across cosmic scales. The second, more disturbing, challenges conventional cosmology. If the universe didn't originate spinning, an unknown force or field must operate on scales far exceeding previous assumptions. A rotating cosmos would entail physical asymmetries, affecting everything from particle physics to the universe's fate. It might also influence dark energy, potentially causing direction-dependent expansion rates, possibly explaining anomalies Webb detected. This discovery raises profound questions about our position within the cosmic hierarchy, hinting that our universe could be one spinning component within an unimaginably vast multiverse. Webb's discoveries didn't stop there. The telescope next revealed black holes forming through previously impossible mechanisms. In the Infinity Galaxy, astronomers identified a supermassive black hole forming via direct gravitational collapse, not from massive star death. Suspended amid glowing hydrogen between two colliding galactic nuclei, this black hole exists where theory predicts none could survive. Normally, merging galaxies' black holes spiral together to form binaries, eventually merging or ejecting one. Infinity Galaxy defies this pattern, hosting a black hole in gravitational no man's land. Pieter van Am and Gabriel Bramah discovered the system in Webb's deep field images. Its figure-8 shape drew attention, but subsequent observations revealed something far more profound. Radio emissions pinpoint a black hole in a location theoretically impossible for survival. Direct collapse functions like a cosmic avalanche. Colliding galactic gas streams became so massive and dense they collapsed into a black hole without forming stars, bypassing standard stellar evolution. This explains Webb's puzzling early universe supermassive black holes, which otherwise appear too mature for their age. Traditional formation requires massive stars to evolve and die over hundreds of millions of years. Direct collapse black holes begin with immense mass, potentially millions of times a stellar mass black hole, allowing rapid growth. Infinity Galaxy offers a real-time laboratory to study this exotic process, with the black hole actively accreting gas from colliding cores, growing as astronomers observe. Yet even this rapid formation cannot explain Webb's next extreme find, a black hole consuming matter at rates physics deems impossible. Hidden among thousands of deep space X-ray sources, Webb detected a supermassive black hole, Li 568, devouring matter 40 times faster than theoretical limits, growing at unprecedented rates, and challenging fundamental black hole physics. Every black hole has what astronomers refer to as an Eddington limit, the maximum rate at which it can pull in matter before the intense radiation pressure from superheated gas prevents further accretion. It's like trying to drink from a fire hose. Surpass a certain flow and the pressure stops you from taking in more. Li 568, astonishingly, appears to be feeding from the equivalent of 40 fire hoses at once. Detecting this phenomenon required Webb's infrared sensitivity combined with data from NASA's Chandra X-ray Observatory. Li 568 was initially hidden among thousands of bright X-ray sources, invisible to optical telescopes, yet blazing in high-energy radiation. Webb's infrared capabilities enabled astronomers to identify faint counterpart emissions, revealing the black hole's true nature. What makes LID 568's feeding frenzy particularly unsettling are the implications for its rapid growth. At these extreme accretion rates, it could have gained most of its mass in a single intense feeding episode. The black hole exists only 1.5 billion years after the Big Bang, when the universe was still very young. Achieving supermassive status this quickly, while adhering to normal feeding limits, would require impossibly large seed masses. Li 5568's extraordinary feeding rate offers a potential resolution to this cosmic timing issue. Observations of the material flowing from the black hole indicate that significant portions of its mass growth occurred during these frenzied episodes, not through gradual accretion over billions of years, but through violent events that rapidly increased its mass. The physics behind such extreme feeding remains poorly understood. Somehow, the black hole stabilizes accretion despite radiation pressures that should eject its fuel. Either the black hole has a mechanism to control radiation pressure, or the surrounding matter has unusual properties that allow it to resist dispersal. LID 568 exemplifies extreme black hole behavior, pushing the boundaries of physics and suggesting that the early universe experienced far more violent feeding events than seen today. These intense accretion episodes could explain how supermassive black holes reached colossal sizes so quickly, growing in short but extreme bursts rather than over billions of years. Yet Li 568's extraordinary feeding is only one example of the strange activity Webb uncovered in the early cosmos. Telescope surveys revealed that the universe's youth was far more chaotic and violent than previously imagined. Massive galaxies appeared dormant in regions where star formation should have been vigorous, defying expectations. Researchers have dubbed these Sleeping Beauty galaxies, enormous star systems that inexplicably ceased forming new stars during their most active periods. Containing billions of stars, these galaxies show no evidence of ongoing star formation, contradicting models of early galactic evolution. The discovery emerged while examining galaxies formed between 600 million and 6 billion years after the Big Bang, a period rich in gas and dark matter, perfect for rapid star creation. Most galaxies of this era should blaze with new stars, consuming gas rapidly to build stellar populations. Instead, Webb found many massive galaxies seemingly in cosmic hibernation. Their stellar masses rival the Milky Way, yet they lack vigorous star formation. They resemble vast cities where all construction abruptly halted. The Sleeping Beauty label reflects this dormant state during peak development, akin to a fairy tale princess in enchanted slumber. Unlike the story, however, there is no obvious cause for their cosmic pause. Several theories attempt to explain this unusual behavior, each challenging assumptions about galaxy evolution. One proposes that central supermassive black holes became so active that their energy output heated surrounding gas beyond star-forming temperatures, a process called active galactic nucleus feedback. However, the timing doesn't align. These galaxies appear to have halted star formation before their black holes reached sufficient activity. Another theory posits that early galaxies consumed their gas so rapidly that they literally ran out of fuel, implying far higher star formation efficiency than modern systems. The most unsettling idea is that unknown processes, unique to the early universe's different physical conditions and higher matter densities, could have triggered the shutdown. The existence of these dormant galaxies reshapes our understanding of cosmic evolution. If massive galaxies could halt growth so early, galaxy formation may be far more complex and unpredictable than thought. These Sleeping Beauty galaxies provide further evidence that the early universe was stranger and more violent than models suggest. Meanwhile, a rogue planet drifting through space revealed an unprecedented atmospheric structure. S0136 plus 0933 defies comparison with any solar system world. Free-floating, illuminated only by its internal heat, it hosts a layered atmosphere where iron rain falls through clouds of magnesium-rich minerals. Webb's analysis shows a cosmic layer cake of metallic clouds at different altitudes. Near the surface, dense iron clouds drive weather unlike anything on Earth, with vaporized metal condensing into liquid iron rain. Higher layers of forsterite, a magnesium-rich mineral, produce separate weather patterns, forming silicate clouds under precise temperature and pressure conditions. The interaction between these layers generates complex atmospheric dynamics beyond conventional planetary science. Infrared observations revealed patchy, shifting cloud layers, indicating active weather powered by the planet's rotation and internal heat. Iron and magnesium clouds circulate differently, creating a three-dimensional atmospheric system. Above both layers, Webb detected hotspots, powered by radio auroras, intense electromagnetic phenomena akin to Earth's northern lights, but at lethal energy levels. These auroras imply an extraordinarily strong magnetic field, far exceeding anything in our solar system, interacting with interstellar charged particles to heat portions of the upper atmosphere beyond the metallic cloud temperatures below. Graduate student Alison McCarthy notes that S0136 demonstrates atmospheric variability mechanisms previously hypothesized but never observed directly. Such complex atmospheric chemistry on a rogue planet raises profound questions about planetary formation and evolution. S0136 has developed and maintained this intricate atmosphere while drifting through interstellar cold, far from any star. Rogue planets may support far more complex atmospheric processes than previously imagined. If one wandering world can host iron rain and magnesium clouds, millions more across the galaxy could harbor similarly exotic weather systems. This metallic rain planet represents a new class of planetary atmospheres, challenging our understanding of possible cosmic weather. Adding to Webb's astonishing discoveries, a galaxy nicknamed the Cosmic Owl reveals violent processes. Initially noted for its owl-like shape, bright central region forming two eyes, surrounding gas and dust resembling feathers, detailed analysis shows it belongs to jellyfish galaxies. These galaxies move through space with extended tentacles of stars and gas, evidence of violent ram pressure stripping, which tears material away as the galaxy moves. Imagine driving a convertible at high speed while loose cargo flies out. The cosmic owl loses parts of itself in transit. Webb's infrared imaging revealed tentacles stretching hundreds of thousands of light years, containing billions of stars ripped from their original homes, now isolated in the tentacles and gradually dispersing into space. Yet the most unsettling feature of the cosmic owl isn't just what it loses, but what the stripping process reveals about galactic surroundings. The ram pressure needed to produce such extended tentacles implies the galaxy is moving through an extremely dense, hot medium, far harsher than the relatively empty space between typical galaxies. This suggests the cosmic web, the vast structure linking galaxies, is far more violent and turbulent than previously understood. Galaxies aren't simply drifting through space, they're battling environments capable of tearing them apart. The jellyfish stripping process also triggers star formation within the tentacles themselves. As gas is removed and compressed by ram pressure, new stars ignite in regions far from the galaxy's main body. The cosmic owl is thus simultaneously being destroyed and seeding fresh stellar populations. Webb's observations reveal active star-forming regions scattered along the tentacles, glowing bright blue with young, massive stars. These stellar nurseries exist in gravitational isolation, billions of light-years from the galaxy that provided the gas. Extensive jellyfish structures in Webb's deep-field images suggest that galactic cannibalism and stripping may be far more common than previously assumed. The universe may host countless cosmic refugees, stars and gas torn from their parent galaxies drifting through intergalactic space. The cosmic owl represents only one dramatic example of the forces shaping galactic evolution on grand scales. Even this galactic violence is minor compared to the stellar chaos Webb observed within individual star systems. Young stars are producing heavy elements earlier than expected, creating cosmic chemistry that defies standard models of stellar evolution. Webb has detected young systems generating oxygen, carbon, and nitrogen at rates that should be impossible for their age. These nurseries are forming complex chemistry that, according to conventional models, should require billions of years of successive star formation and supernova events. The key factor is metallicity, the abundance of elements heavier than hydrogen and helium. In the early universe, only hydrogen and helium existed in significant amounts. All heavier elements, from carbon and oxygen to iron and gold, had to be forged in massive stars and dispersed through supernovae, a process that normally takes time. The first-generation Population 3 stars consisted almost entirely of hydrogen and helium. When they died, they enriched the surrounding space, allowing subsequent generations of stars to form with more complex chemistry. Webb has discovered systems that appear to skip several steps. Galaxies less than 1 billion years old already show metallicity levels requiring multiple generations of stellar evolution. They are producing heavy elements at rates inconsistent with their apparent age. The most extreme case is galaxy JWST 131, observed just 330 million years after the Big Bang. Spectroscopy revealed bright hydrogen emission lines and evidence of substantial heavy element production, indicating significant stellar evolution in the universe's infancy. This extraordinary chemistry forces a re-evaluation of early star formation assumptions. Either the first stars were far more massive and short-lived than current models predict, rapidly creating and dispersing heavy elements, or an entirely unknown mechanism enriched the early universe with complex chemistry. The first scenario suggests Population 3 stars were colossal, hundreds of times the Sun's mass, burning fuel in a few million years before exploding in hypernovae and scattering heavy elements across vast distances. Such stars do not exist today, but the extreme conditions of the early cosmos may have permitted their formation. The second possibility is more unsettling. Unknown processes could have generated heavy elements independent of standard stellar nucleosynthesis, implying our understanding of cosmic chemical evolution is incomplete. This accelerated metallicity evolution also affects planet formation and potential early life. If heavy elements were available sooner, rocky planets and the chemical precursors for life could have emerged much earlier than previously believed. The early universe may have been chemically far more sophisticated than models suggest. A planet orbiting Alpha Centauri A, the Sun's nearest stellar neighbor, has baffled astronomers by appearing and disappearing in Webb's observations. This enigmatic detection, the telescope's most startling to date, suggests a giant planet roughly Neptune-sized within the star's habitable zone vanished entirely during follow-ups. Several hypotheses attempt to explain this cosmic vanishing act. One proposes an extremely elliptical orbit, bringing the planet close enough to detect only briefly. However, gravitational interactions with Alpha Centauri b make such an orbit unlikely. A second theory suggests the planet is real, but occasionally obscured by a variable dust cloud or debris ring, implying a dynamically active system with collisions and shifting material. A third possibility is that the signature originates from a forming planet accreting material episodically, alternately visible and invisible. The most disconcerting idea is that the thermal signal represents a previously unknown phenomenon, such as a warm debris cloud or failed star formation event in Alpha Centauri's outer regions. This vanishing act highlights how little we understand about planetary systems, even nearby ones, and suggests that other phenomena may remain hidden in plain sight. Webb has also uncovered ancient magnetic fields spanning the cosmic web, exhibiting complexity akin to human brain networks and predating any other known structures. These primordial fields appear to originate from the universe's first billion years, when large-scale structures were still forming. Observations show filaments of gas and dark matter stretched across hundreds of millions of light-years, threaded with intricately connected magnetic networks. Their organization is strikingly brain-like, with nodes and hierarchical connections resembling neural structures, prompting researchers to apply methods from neuroscience to analyze cosmic magnetism. These magnetic fields challenge conventional assumptions. Standard models predict gradual field development via stellar winds and supernovae over billions of years, yet these primordial networks existed long before such processes. They may have influenced early galaxy formation, shaping gas collapse, stellar masses, formation rates, and chemical evolution in ways current theories cannot explain. Most strikingly, the brain-like networks suggest the early universe developed organizational complexity far earlier than expected. Rather than mere gravitational collapse, cosmic evolution may have functioned like a vast information processing system. These fields are dynamic, with connections forming and breaking over cosmic time. Webb also detected magnetic storms spanning galaxy clusters capable of influencing star formation and galactic evolution on unprecedented scales. The discovery holds significant implications for understanding dark matter and dark energy, as magnetic interactions can affect matter distribution across the cosmos. If the primordial magnetic fields were far more intricate and potent than current models suggest, they could account for some of the anomalies James Webb has uncovered in cosmic structure formation. These brain-like magnetic networks pose a significant challenge to our understanding of how complexity emerges across the universe. If such highly organized structures existed in the early cosmic web, it indicates that the universe may possess innate tendencies toward complexity that we have not previously recognized. These ancient magnetic fields might hint that the universe has characteristics similar to living systems, with information processing and organizational capabilities arising from physical processes that remain largely mysterious. At the center of our galaxy, a supermassive black hole pulses with irregular rhythms that point to unknown physics at the limits of space-time. Sagittarius A, the 4 million solar mass black hole residing at the Milky Way's core, has long intrigued astronomers. Continuous observations by James Webb have revealed unprecedented phenomena. The black hole exhibits erratic luminosity fluctuations, resembling a heartbeat with no discernible pattern. Using Webb's near-infrared camera, scientists monitored Sagittarius A for 48 hours across multiple sessions throughout a year. Their findings revealed a black hole in perpetual flux, its accretion disk producing a continuous yet chaotic sequence of brightness variations punctuated by sudden dramatic flares. The observations highlighted constantly shifting, bubbling luminosity near the black hole's event horizon. Abruptly, immense bursts of radiation would erupt from the accretion disk, only to subside again. These flares appear completely random, defying attempts to detect underlying patterns or periodicity. Farad Yusuf Zard, leading the study at Northwestern University, described the behavior as unlike anything previously observed in supermassive black holes. The absence of predictable patterns suggests that the physics driving these brightness fluctuations exceeds the scope of current models. Two processes appear to generate this cosmic heartbeat. Short-term variations likely stem from turbulence in the accretion disk, where magnetic interactions compress plasma and produce fleeting flashes of radiation, akin to cosmic lightning spiraling toward the black hole. However, the larger flares hint at more extreme dynamics, potentially caused by massive chunks of matter crossing the black hole's photon sphere, the region where light begins orbiting before either escaping or being irreversibly consumed. This irregular activity indicates that Sagittarius A star is far more active than previously assumed. Unlike the slowly feeding, relatively quiet monster described in textbooks, the Milky Way's central black hole seems locked in constant low-level violence, consuming matter in unpredictable bursts. The implications for black hole physics near the event horizon are profound. These brightness fluctuations originate in regions where gravity severely warps space and time, creating conditions where matter and energy behave in ways that push general relativity to its limits. The chaotic nature of these variations hints that quantum effects might influence accretion. Near the event horizon, classical and quantum boundaries blur, potentially giving rise to phenomena unseen elsewhere in the cosmos. This cosmic heartbeat raises questions about the fate of information entering black holes. If the accretion disk's behavior is genuinely random, it could suggest that black holes destroy information in ways that challenge fundamental quantum mechanics. Sagittarius A's irregular pulsing provides our closest observation of physics under extreme conditions, where gravity warps spacetime so intensely that its fabric begins to break down. Invisible forces are molding cosmic structures through violent processes, shredding galaxies and scattering their stars across millions of light years. James Webb has found evidence that dark matter, the mysterious component making up 85% of all matter, engages in violent interactions capable of tearing galaxies apart and reshaping cosmic structure on vast scales. These dark matter catastrophes are invisible except for their gravitational effects on ordinary matter. Observations of galaxy clusters, where hundreds of galaxies are bound by dark matter, reveal collisions unleashing energies comparable to billions of supernovae. Webb's detailed imaging shows that such violence extends far beyond collision zones. Galaxies millions of light-years away show signs of gravitational disruption, only explicable through dark matter interactions on previously unimaginable scales. The telescope detected extensive stellar and gas streams connecting galaxies across vast distances, forming bridges between separate systems. These streams represent remnants of galaxies gravitationally shredded by dark matter during cluster interactions. What makes this cosmic destruction particularly striking is its hidden nature. Normal matter interactions produce visible electromagnetic signatures, but dark matter collisions emit no light, heat, or radiation. Only gravitational effects betray their existence. Webb's infrared sensitivity reveals the full extent of this hidden violence. Faint stellar streams and tidal tails stretching millions of light-years, forming spiderweb-like structures of disrupted matter undetectable to prior instruments. Each stream represents a galaxy partially or completely dismantled by dark matter forces. The scale of this destruction implies that dark matter is not a passive scaffold, but actively reshapes the universe, ejecting galaxies from clusters, stripping their gas, and scattering stars across intergalactic space. Simulations indicate these events may be central to cosmic evolution. Dark matter particles can collide and interact gravitationally, generating shock waves propagating through the cosmic web and influencing galaxy formation over enormous regions. The hidden violence also challenges our understanding of dark matter's nature. If it participates in such energetic interactions, it might possess properties beyond mere gravitational attraction, possibly undergoing phase transitions or interacting through unknown forces. The discovery of widespread dark matter violence also impacts our grasp of galaxy evolution and cosmic structure formation. If galaxies are continuously disrupted and reformed by dark matter, the universe may be far more dynamic and chaotic than previously thought. These invisible catastrophes reveal a fundamental aspect of cosmic evolution operating entirely outside direct observation, shaping the universe through consequences we detect only after the fact. These unseen catastrophes illustrate a fundamental element of cosmic evolution that unfolds entirely beyond our direct observation, shaping the universe through destructive forces detectable only by their aftermath. A distant galaxy bends space-time so dramatically that it appears in multiple positions simultaneously, producing gravitational effects that test our understanding of general relativity. James Webb discovered a galaxy so massive and dense that its gravitational pull generates several images of itself across the cosmic sky, each revealing the same star system at different stages of its development. This extreme gravitational lensing demonstrates space-time curvature operating at levels that push Einstein's general relativity to its limits. Strong gravitational lensing occurs when an object's mass warps the fabric of space-time like a cosmic magnifying glass. Light from more distant objects follows these curved paths, creating distorted or multiple images that can appear in unexpected places across the sky. Yet this particular galaxy produces lensing effects far more intense than any previously observed. Webb detected at least 4 distinct images of the same background galaxy, each magnified differently and displaying the star system at varying epochs in its evolution. The gravitational field is so extreme that light takes differing amounts of time to traverse each curved path, producing a time delay effect that allows astronomers to observe the galaxy's history unfolding in multiple versions simultaneously. One image shows the galaxy 800 million years ago, while another reveals its structure 1 billion years in the past. This lensing galaxy effectively forms a cosmic time machine, displaying stellar evolution across multiple epochs. What makes this finding especially striking is the implied mass distribution necessary to produce such severe space-time curvature. The galaxy must contain dark matter concentrations far denser than predicted by current models. Webb's observations indicate dark matter clumps and voids, revealing complex internal dynamics that challenge standard cosmological assumptions. Instead of smooth halos, the dark matter appears organized into structures that suggest previously unknown mechanisms. Time delay measurements between lensed images offer direct evidence of space-time curvature following general relativity, yet the extreme nature of the lensing suggests regions where quantum gravitational effects may influence classical geometry. This discovery implies that extreme gravitational environments might be far more common than previously believed. Additionally, the lensed galaxy itself shows rapid evolution, with star formation rates varying significantly between observed epochs. This provides unprecedented insight into galactic evolution during active phases. The so-called time warp galaxy functions as a natural laboratory for studying general relativity under extreme conditions, illustrating how massive objects can reshape space-time geometry. These gravitational effects occur on scales where classical physics begins to break down, hinting at phenomena existing at the boundary between general relativity and quantum mechanics. Across the universe, stars are devouring companions in feeding frenzies violent enough to produce entirely new classes of cosmic explosions. James Webb has captured direct evidence of stellar cannibalism, revealing that binary systems frequently end in catastrophic events where one star consumes its companion. These violent episodes generate explosions that can outshine entire galaxies. The process begins as 2 stars orbit closely, their outer layers interacting. The more massive star gradually strips material from its companion, forming streams of superheated gas spiraling inward in luminous accretion disks. What begins as a slow feeding process can abruptly accelerate into catastrophic consumption. Webb's infrared vision has revealed these frenzies in unprecedented detail, peering through gas and dust that typically obscures such events. Matter streams from the victim star to the predator in complex gravitational dances, culminating in stellar cannibalism. The most extreme examples involve white dwarfs, dense stellar remnants roughly Earth-sized but with solar mass. When these accrete material, they can trigger thermonuclear explosions called Type Ia supernova, temporarily outshining billions of ordinary stars. Even more violent are events involving neutron stars and black holes, which can produce kilonova explosions, synthesizing heavy elements like gold and platinum while emitting gamma-ray bursts detectable across billions of light-years. Webb has traced the full life cycle of stellar cannibalism, from initial mass transfer to explosive events dispersing heavy elements throughout space. Equally concerning is how common these events appear to be. Surveys suggest stellar cannibalism may be a critical driver of cosmic chemical evolution, producing and distributing elements essential for planet formation and potentially life. The violent nature of these events influences nearby stellar nurseries, triggering or suppressing star formation across vast regions and impacting galactic evolution on scales far larger than the original binary systems. Webb has also observed failed cannibalism, where binary systems begin feeding but are disrupted before catastrophic outcomes, creating exotic remnants unlike any in our local galaxy. The prevalence of stellar cannibalism forces a reconsideration of binary star evolution's role in cosmic chemical development. Stars rarely live isolated, peaceful lives. Many engage in violent interactions ending in explosive events. These frenzies represent a primary mechanism through which the universe produces and distributes heavy elements necessary for complex chemistry and life. Evidence is mounting that space-time itself may break down on cosmic scales, revealing cracks that challenge fundamental physics. James Webb's most unsettling discovery may not be a single object, but the cumulative evidence indicating that space-time becomes unstable under the extreme conditions found throughout the cosmos. The telescope has uncovered gravitational irregularities, unexplained energy emissions, and structural anomalies, indicating that the smooth fabric of space-time envisioned by general relativity may be far more fragile than previously imagined. Evidence comes from multiple Webb surveys. Gravitational lensing near massive objects shows slight but consistent deviations from predicted general relativistic behavior, suggesting that space-time may fracture under extreme gravitational stress. These anomalies appear around black holes, in galaxy cluster cores, and near other enormous cosmic structures. Quantum mechanics predicts that space-time at the tiniest scales is turbulent and foamy, with virtual particles and energy fluctuations creating a chaotic quantum foam beneath smooth classical geometry. Webb's observations suggest this quantum foam might manifest on macroscopic scales under extreme conditions. The telescope has recorded unexplained energy emissions from regions where quantum effects should be negligible, including mysterious radiation from black hole event horizons and unusual heating in galaxy cluster cores. Such phenomena could reflect quantum foam interacting with classical spacetime during violent cosmic events. Particularly striking are Webb's observations of cosmic strings, theoretical one-dimensional defects in spacetime that may have formed during the universe's earliest moments. If real, these structures represent fundamental tiers or folds in spacetime, challenging our understanding of cosmic geometry. Several candidates for cosmic strings have been identified, including gravitational lensing patterns inexplicable by known matter distributions, suggesting permanent scars from the universe's turbulent birth. Webb has also detected potential vacuum decay events, regions where the quantum vacuum may transition to lower energy states, releasing tremendous energy. These may indicate fundamental phase changes in reality itself. Altogether, these findings imply that the universe may operate closer to the edge of physical stability than previously thought. Extreme gravitational fields, high energy densities, or exotic matter states could render the fundamental structure of spacetime unstable. Such quantum foam breaches have profound implications for cosmic evolution and the ultimate fate of the universe. If spacetime can destabilize naturally, reality itself may be more transient and fragile than assumed. The presence of quantum effects on cosmic scales suggests the boundary between quantum mechanics and general relativity may be more permeable than theory predicts, impacting our understanding of black holes, cosmology, and the very nature of reality. The coordinated rotation of galaxies and peculiar cosmic expansion patterns hint at an even more astonishing possibility, that our observable universe could reside within a black hole embedded in a larger cosmos. Webb's discoveries suggest that the universe itself might be the interior of a massive black hole. This black hole cosmology could explain Webb's puzzling observations, such as coordinated galaxy spins and expansion rate anomalies. Galaxy rotation patterns observed by Webb show galaxies millions of light-years apart spinning in coordinated directions, something impossible without a preferred universal rotational axis. In black hole cosmology, this alignment arises from our universe inheriting the angular momentum of its parent black hole. The theory posits that the Big Bang may have been our universe crossing the event horizon of a massive black hole in higher dimensional space. From within, this crossing manifests as cosmic expansion. From the larger universe, we fall toward the black hole singularity in a process stretched to infinite time by gravitational time dilation. This explains the apparent accelerating expansion attributed to dark energy. As we descend further into the parent black hole, space-time curvature intensifies, creating the illusion of acceleration while we approach regions of stronger gravitational distortion. Webb's detection of primordial black holes predating star formation fits this model. These ancient black holes may have existed in the parent universe prior to our horizon crossing, appearing in our universe's history as primordial objects predating normal matter collapse into stars. Coordinated galaxy spins across vast cosmic distances align perfectly with the notion that our universe inherited rotation from a parent black hole. The observed expansion discrepancies may arise from measuring different aspects of motion within curved spacetime inside this black hole, producing apparent contradictions. If black hole cosmology is correct, all observable phenomena, from the cosmic microwave background to the most distant galaxies, exist within the event horizon of a massive black hole. We would be forever isolated from the larger universe, unable to influence or communicate beyond our cosmic prison. This theory also suggests that black holes throughout our universe may contain entire universes, forming a nested hierarchy where each black hole could host a separate cosmic realm with its own physics, evolution, and potentially life. Such a perspective redefines our cosmic significance, portraying our universe as one bubble in an infinite multiverse of black hole-contained universes. Webb's findings do more than challenge conventional cosmology. They fundamentally reshape our perception of the universe and humanity's place within it. Long-held assumptions about galaxy formation, black hole behavior, and cosmic expansion have been upended. Webb reveals a cosmos populated by impossible objects, violent processes, and phenomena governed by physics beyond our understanding. The universe is not the orderly, predictable domain of textbooks. It is a realm where galaxies form faster than expected, black holes roam naked through space, and space-time itself may be unstable. Humanity does not dwell in a cosmic garden conducive to life, but within a violent arena where reality can collapse under extreme conditions. Perhaps most unsettling is what these discoveries imply about our isolation within this cosmic framework. If we truly inhabit a black hole universe, as mounting evidence indicates, then we remain permanently isolated from any larger reality that may contain us. Every message we send, every probe we launch, is confined within our cosmic prison. The prevalence of violent phenomena that Webb has revealed further underscores the fragility of our long-term survival. The cosmos teems with wandering black holes, rogue planets emitting unexplained signals, and stellar cannibalism events capable of sterilizing entire regions of space. Our galactic environment may be far more hazardous than previously understood. The rapid discoveries also highlight how little we truly know about the universe we inhabit. Despite centuries of astronomical study, Webb's initial years have uncovered phenomena that demand a profound re-evaluation of cosmic evolution. If we have been so mistaken about fundamental processes, what else have we overlooked? Observations of early galaxy formation and primordial black holes indicate that the universe reached complexity much sooner than once thought, suggesting that cosmic evolution could follow pathways previously unconsidered, potentially including the emergence of intelligence and civilization under unexpected conditions. Yet Webb's findings also inspire optimism. The universe's capacity for unpredictability and complexity implies that cosmic evolution may be far richer and more varied than our models predict. If reality can produce seemingly impossible galaxies and exposed black holes, it may likewise generate forms of life and intelligence governed by principles we have yet to understand. The telescope has effectively shown that we are cosmic infants in a universe whose rules we are only beginning to perceive. Every unusual object Webb identifies, every extraordinary phenomenon it reveals, offers a chance to expand our grasp of what is possible in a cosmos that consistently defies expectations. Most importantly, these discoveries remind us that the universe owes us no clarity. Reality functions according to its own logic, often fundamentally alien to human intuition. Our species' survival and progress depend on adapting our understanding to the universe as it truly exists, rather than as we imagine it. The cosmos unveiled by James Webb is strange, violent, and often unfathomable, yet it remains the only reality we possess, and comprehending it, even when unsettling, offers our best hope for navigating the cosmic future ahead. Thank you for watching, and we hope to see you in the next video. Please make sure to follow the DocuVerse channel.